Okay, it's 2 p.m. So welcome again to another Penn seminar. Today we have the pleasure to have Dr. Tom Van Dam here. So Dr. Van Dam is a principal at Janney Elstner Associates. His research focuses on low carbon concrete, Portland cement, alternative cements, supplementary cementitious materials, concrete durability, and concrete pavement materials design, construction, and evaluation. He earned a doctorate, master's, and bachelor's in civil engineering from the University of Illinois Urbana-Champaign. So let's welcome Dr. Van Dam.
Well, first of all, thank you, and thank you for having me. I spent a lot of years here. Is this too loud? Is it all right? Sound fine? Sound check's good. Excellent. I started undergrad in '79, so it gives you some idea how old I am. And I guess hopefully there's some relevance still to some things I have to say. I was telling Jeff at lunch, one thing that's important to me is never get bored. And so I'd encourage all of you to have that same attitude. Never get bored. Never be satisfied with just turning the crank on something, but instead always find engaging work, because there's a lot of things for us to do. That's very, very interesting. A little bit, I feel compelled at least to do a little salesmanship on my company. I think some of them are listening. So, hey guys, thumbs up. This is the little thing at WJE. I've been with the company about 2.5 months. So this is a new gig for me. I actually can say with honesty, it's been great. It's an amazing place to work. Janney's been around since 1956, and they're really focused on problem solving, which is what I do and like to do. So obviously with Janney, Elstner has completed numerous investigations, testing, more than 175,000 projects have been completed to date. And what I like about the company is we get the most interesting work, right? We don't get the mundane work. We get the stuff that others maybe it's beyond their capabilities, or it's just they'll turn to us to help them solve that. You can see pretty good geographic distribution around the U.S. with one office in London. I got to figure out how to work out of that office at some point. And this is what really drew me in, is the Janney Technical Center. I am a lab rat at heart, and that strong floor may look a little bit familiar to you in that it was modeled on the one at the University of Illinois. So Janney is packed with Illinois grads. This strong floor is super busy. We have a full machine shop. They offered to teach me how to weld, a full wood shop. They took one look at me and said, don't get anywhere near our saws. And but that's great. But what I really enjoy is I've done a lot of work with petrography. So the petrography labs, the electron optics are good. The analytical capabilities are fabulous. And so, we can do work that almost no other commercial lab can do. And it rivals or exceeds most universities, maybe U of I with exception. I think a brief personal history is probably important. I've been doing this for like 35 plus years. Not only did I do my bachelor's, master's, and PhD here, my daughter did her bachelor's and master's. They got her master's under David Lane. So it's almost a family affair. She then went to Michigan to disappoint me and got a law degree, but what am I going to do? I'm a recovering academic, which means basically I was a tenured faculty at Michigan Tech. I was going up for full professor after 12 years, and I quit. So shows how little patience I have. And I've been working as a consultant since 2008. My primary work has been on pavements and slab on grade, and then concrete materials. I've chaired ACI Durability Committee. I'm now at the ACI TAC, Technical Activities Committee. I'm involved with a lot of committees at ACI and others. About 2010, I really started gravitating into sustainability. So I've been a principal investigator on the FHWA Sustainable Pavements Program with a mod for all those years. We continue to work on that program. And then really, in the most recent years, have gravitated in this area of carbon reduction. The last thing is the personal stuff. I recently became a grandfather. very important and gives my work a lot of relevance in trying to work towards low carbon. I break other people's sailboats for fun. If any of you are sailors, you know what that means. You don't want to have your own boat. You want to sail on other people's boats. So when stuff breaks, they have to pay for it. And then I'm also a Black Rock Ranger at Burning Man. So that's one of the things I do in my hobby. And if you don't know what that is, that's all right. But I wasn't there this year, so I missed the apocalypse. So why are we here? You know, what is the driver for this conversation? And the driver is climate change. And you know, the end is near has been around for a long time. Even when I was a kid, this is the hippie that was marching around with the sign. The end is near in the 1960s. And I like this idea, can you be more specific? So when we look at climate change, you know, and I give this talk or some element of this talk to trade organizations. I've had people swear profanities at me in Iowa. I assume with an educated group such as yourself, I won't necessarily have to do much apologetics here, but basically scientific observations are confirming climate is changing. You know, the melting in the Arctic is indisputable. Sea level rise is well documented. Hurricanes, wildfires becoming more severe. And this recognized climate crisis or impending climate crisis has got government policy orientation now. So there's a lot of investment coming from federal government through the Infrastructure Investment and Job Act and the Inflation Reduction Act to address climate change issues. And I'll get to some of those towards the end. Low carbon solutions, as a result, are really of a lot of interest. And this is not just a US issue, right? I see in this group here a lot of students from around the world, right? This is an issue in your countries, right? Am I right? This is going on all over. This is not just the Democratic Party in the US pushing this agenda. This is a concern worldwide. And if any of you are from like Bangladesh, it's of acute interest to you, or an island nation where sea level rise is definitely causing immediate threat. The driver behind a lot of this, and this is just looking at atmospheric carbon dioxide, one of the most common greenhouse gases, not the only one, but this is looking back 400,000 years in ice cores and projecting carbon dioxide in the atmosphere. You can see a dramatic spike has occurred since about 1850, since the Industrial Revolution. This is actually measured data, and this everyone can gravitate towards. This is on mountaintops in Hawaii. They actually had to move it off of Mauna Loa recently because of volcanism, and it's actually stopped recording data for the last like 10 days, I think, due to the wildfires, I'm guessing. But regardless, this is a precipitous increase in carbon dioxide. This is the data since August 5th. A lot of scatter, but you can see this trend line. And then as of the last date that they have recorded data, August 27th, we're at 420 parts per million at that date. So it bounces around a little bit seasonally, but this upward trend is an indisputable fact, and it's causing a lot of havoc. Oops. The linkage between that increase in carbon dioxide and global warming are shown here. You know, we're warmest multi-century period in 100,000 years occurring now. This is an unprecedented warming in the last 2,000 years. And then if we simulate the increase in temperatures, taking out solar and volcanic, or looking, simulating natural only, looking at the impacts of volcanism and solar activity, you'll see it's pretty flat line. We see some variations, but generally flat line. But basically, if we bring in the effects of greenhouse gases, this is where that trend increase occurs. You know, this is just kind of projections over time of where we think things could go. The bottom line is that even if we stop now and could pull back, we could moderate. But if we keep doing business as usual, we expect to see possibly up to 2 to 3 degrees centigrade rise by 2100, which could be devastating as far as ocean rise and climatic impacts. And I just want to emphasize, it isn't something that's going to be uniform across the globe. We're going to see changes in temperature patterns. which will all be getting warmer, but some areas like the Arctic is really cooking. But other things we're going to see are changes in precipitation patterns, which are, a fairly dramatic concern if you look at the areas that are going to be dry. Sub-Saharan Africa, for one, is looking pretty serious. The Southwest U.S. is another area where drought is going to become pretty acute. And that leads to wildfires, leading to extreme storms. And all of this is my really downside of the talk, but it's why we're here and why the mind is focused. So what we have in front of us is a challenge, right? Change is a very difficult thing. And most of you are young, but when you've been working in the concrete industry as long as I have, or any industry, to get them to change, it's a monumentally difficult task. Traditional cement and concrete are carbon intensive, and I'll talk about that. And designs and materials are really dictated by the past and conservatism in codes and specs, and it's really dictated about what we've always done. And our own code of conduct as civil engineers are basically we have to more or less do the same thing a person in our position would do in this place at this time, right? Our own, standard of care is not one to innovate. So this idea of trying to innovate and do something different is a difficult thing, but there is tremendous opportunity. And that's what I think is super exciting. So one thing that was done is PCA about, I think 2 years ago now, they came out with a roadmap. They've since updated it, I believe, once, but it's a roadmap to carbon neutrality. So the Portland cement industry in the US is committed to being carbon neutral by 2050. So many other people have committed to this. And the very goal is that we need to see some pretty gradual but dramatic changes by 2035. And then it's what I call then fusion happens. And we have all the free energy in the world and we can sequester CO2, right? Because we're kind of, the problem we run into is about 2035. But in the meantime, we can get about a 40–50% reduction pretty easily through a lot of strategies. So why is hydraulic cement concrete so important? Basically, we use about 2 cubic yards of concrete per person on the planet every year. That's about, 8,000 pounds of concrete is getting used worldwide. And that's a lot of concrete. The reason we use so much is civilization is built with it. If you don't believe me, look around you. These walls, that column, the foundation, the sidewalk, the curb and gutter. Occasionally we give the asphalt guys a pavement or two to build, but everything else is basically built out of concrete. And, there's always a big thing about concrete pavement versus asphalt pavement. 6% of the cement we use in the United States goes into pavement. 6%. Another 18% goes into the infrastructure within the highway network. So roughly 24% of cement we use in the US goes into the highway right-of-way, into curb, gutter, sidewalks, sewers, foundations, bridges, barrier walls, you name it. We use concrete for everything. As a result, 5–8% of global greenhouse gases are associated with the production of concrete. Very large economic, environmental, social impacts. We make 92 million metric tons of cement in the US every year. We import roughly another 20 million metric tons. So that's how much we're using on an annual basis. In the US, it's about 1% of our greenhouse gas emissions, just for making that little gray powder that is so common. It's important to emphasize, though, that if we look at it on a mass basis, concrete actually has one of the lowest carbon footprints and embodied energies. It's all the way down in this region here. It's just that we use so much of it. We're even stabilizing stuff with it now, right? We're using it for bases. We're using stabilized soil. It's used everywhere. So that is our issue. Why is there so much CO2 with this? Basically, it's very simple. We're putting limestone into a kiln and we're burning it. Limestone is calcium carbonate. calcium, calcium CO3. We're driving off CO2 to get calcium oxide. Calcium oxide reacts with silica and alumina to give us Portland cement. So 46% of all of the CO2 associated with manufacturing concrete, this is concrete, not just cement, 46% is from calcining limestone. So no matter what we did on energy efficiency, in grinding efficiency, and in concrete production, and everything else, we still got basically this big thing right here from burning the limestone, driving off the CO2. And ultimately, that's going to have to be captured. Okay, they're going to have to capture that and do something useful with it. Roughly in the US, for every pound, kilogram, metric ton of cement that we manufacture or sell, I should say, roughly 0.922 pounds, kilograms, metric tons of CO2 is produced. And so you hear people say for every ton of cement, there's a ton of CO2. That's pretty good, not a bad estimate. A little bit less, we're getting better, but that's the reality. So that's what we're confronted with. We take that cement, we combine it with gravel, sand, water, admixtures, and typically we're going to end up on average in the US with some SCMs, about 359 kilograms CO2 equivalent through cubic yard. And people hate the mixing of the units here. I mean, it's not often you're going to see kilograms per cubic yard, right? That's the way you do it. When we're talking about CO2, CO2 is always reported in kilograms equivalent. That's how you report it. So you never talk about pounds of CO2. And that's just because it's the ISO standards. And so get used to that unit for whatever you apply it to. And out of that 360 roughly, 320 kilograms CO2 equivalent is from the cement. So we know what the problem is here. And if we consider a problem, right? The problem is the very thing that we use as the glue, which is holding all this mess together, which is Portland cement. So how do we work strategies to reduce this? So how do we change our industry? The whole key is to get clinker out of concrete, right? This clinker that comes out of the end of the kiln that has all that embodied CO2, we need to use less of it. So we can do this two ways. One is optimize the cement. The second way is to optimize the concrete. And together, you know, we could probably shave off 40% of our carbon footprint without going to any new material or technology, strictly by better engineering using what we have. That doesn't come, though, without challenges. Challenges are extremely difficult. Change is extremely difficult for our industry, very difficult. So we actually put a report together, the we being Larry Sutter. Some of you might know these folks. He used to be Associate Dean of Michigan Tech. Also, he was my PhD student, the only one I graduated. Shows what a lousy academic I was. And then we have Doug Hooten from University of Toronto, Emeritus, and then Al Innes, who is former Vice President of Holcim Cement, put a report together for Breakthrough Energy Foundation. And if you want a copy of the report, please email me. It's called, we completed this report called Removing Barriers to Rapid Adoption of Carbon Reduction in Concrete. And then we have an article coming out soon in Concrete International. But the two general approaches for reduction, we spent a lot of time in that is talking about the barriers. And briefly, I'll mention the barriers are not what you would think. Our initial approach was the barriers were going to be the specs. The barriers were going to be, code. The barriers are risk. That's where the barriers lie. The barrier lies if we change something, who's going to bear the risk of that change? And take out life safety, right? We're not going to compromise life safety, but if I make a change and a DOT says now, hey, we're going to take 50 pounds of cementitious out of our mix, the one who bears that risk now is the contractor, right? The risk boils on the contractor, and the contractor's going to do one of two things. They're either not going to bid it, or they're going to bid it at a really high price. And so that's what we have is where you come to. But the two things that I'm going to focus on the rest of this talk are substitution, partial replacement. If I could talk, I would say that better, of Portland cement with alternative materials, and reducing total cementitious content. So when we get strategy one, get the clinker out of cement. Many of you who are working in this, how many of you work with, well, how many of you are working with concrete right now? Like 2 of you, 3 of you? 3, awesome. You probably haven't realized a revolution occurred in the last 2 years. In this market, you went from ASTM C 150 type 1-2 cement to ASTM C 595 type 1L. And for some of you, this happened overnight. And a rippling effect, right? Because test methods that you have that are devised to work with Portland cement were not devised to work with Portland limestone cement. Everything changed overnight like that. So what has happened is the cement industry is responding. They're starting to blend limestone in with their clinker. And so this movement from, instead of just blending at the concrete plant, SCMs like fly ash or slag, you're going to see more and more blending happening by the cement companies. They're going to start selling blended product. And this replacement, as I said, of the 595, ASTM C 595 type 1L, it can blend up to 15%. And the reason they selected that is actually, when you start to put in limestone and you intergrind it with clinker, you actually get a more optimized binder, and you see an improvement in strength and a decrease in porosity. And up to about 12–13%, as the chart there shows, in this case, you're about even with where you started, and that's how that number was selected. I don't have a lot of slides on the science of this. This is an overarching practical talk, but the bottom line is if you study this and you couple this with clays or aluminate sources from an SCM, you'll actually get another phase formation, carboaluminate formation, and you actually get a synergistic relationship. So when you take a blended blended limestone cement and you blend it with a fly ash, with high alumina or slag or a calcined clay, you actually will see added benefit. So traditionally, when we looked at these supplementary cementitious materials, fly ash is top of our list. Uh-oh. It's an important call, I'm sure. It's not. I'll tell them I'm giving a talk. Mute your cell phones, by the way, whenever you're giving a talk. So fly ash is collected when we burn pulverized coal in a power plant. We collect the ash through electrostatic precipitators. This ash is a glassy, wonderful supplementary cementitious material. Do you think we're burning more coal today than we were 10 years ago? What do you guys think? In the US? No, in the US we are not, right? We're burning less. We're going to burn less 10 years from now? Absolutely. Is there a shortage of fly ash coming right from a power plant? You bet there is in a lot of places around the country. So our traditional source of fly ash is diminishing at the same time we need it to knock down our carbon footprint. Now we could argue about, well, geez, if you're burning coal to get your SCM, how is that reducing your carbon footprint? That's a good talk. And it's actually, it's completely relevant talk. But we can't give that talk now. Slag cement, same thing. Slag cement made from blast furnace, iron blast furnace slag. You take it, instead of taking that slag and running it into a pit and allowing it to air cool, you run it and quench it in water through a granulator, create something that looks like sugar that you then grind up, and it's a fabulous cement on its own or with an alkali activator, such as Portland cement. How about blast furnaces? Are we building more blast furnaces in the US right now? Not so much. We're granulating about every source of slag cement that's economically viable to do so right now. So you're not going to see more of that. We're going to import more, but you're not going to see it being manufactured here. And the final one is natural pozzolans. Calcined clay, volcanic ash, brown pumice. These are a growing market. Lots of natural pozzolans are starting to come online. As we move towards these blended cements, I talked about the 1Ls, which are here. but we also have a 1P, so that could be pre-blended with a pozzolan, a 1S, a 1T. And the charts on the left, they show basically, I think that was 2018, green was the number of states that accepted Portland limestone cement. And just a few years later, you can see the change in 2022, so 4 years. That's an acceptance in the spec. More telling is the trend here showing basically, this is the cumulative total amount of blended product available in the US. So back in 2021 in January, 3% of the cementitious material sold in the US was a blended cement. And today, we're actually close to 40%. This is from October 2022. So we're approaching 40% now in the US. It is guessed that by another 4 or 5 years, it'll be 80% or 90% will at least be Portland limestone cement. So as I mentioned, we don't have any new sources of fly ash and they're going down. We're not going to have any new sources of slag, they're going down. So where are we getting this supplementary cementitious material? The one thing we're doing now is we're reclaiming coal ash from landfills. So we're actually going to start doing more and more. And Jeff, I think you said you had a project with reclaimed ash?
Municipal solid waste ash.
Solid waste ash, another source. But they're mining landfills and ponds. You got to process it because it's combined with bottom ash. And if it's a pond, it has a lot of dead ducks, seagulls in it, you know, things of that type because the pond was out there in the waterfowl. But you got to process that. You guys are having like no humor at all. You're too serious for students. Seriously, you guys gotta relax, man. The world is your oyster. This is the best times of your life. No, it's not. But believe it is. Life keeps getting better as long as you allow it to. Basically, we're going to mine this stuff. We're going to have to process it, and it's being sold and it's being used. And there is 150 to 200 years of ash available. But it does come now with a little bit more of a footprint, right? Whereas ash is a waste, it's garbage. It either gets used or goes into a landfill. Thus why it doesn't count as having a carbon footprint for the concrete. If I mine it and I process it, that mining and processing have to get counted towards its carbon footprint. It will still be low, but it will count. Ground bottom ash. This is a separate item of its own. Again, it fits under ASTM C618 now. A year ago, neither one of these fit under ASTM C618. This was a big change. This is the biggest change in the fly ash spec probably in 20, 30 years. Adding the idea of changing it from fly ash to coal ash. And big change and big progress at ASTM. There's also an ASTM standard now for ground glass pozzolan. Bottles, right? How many bottles are out there? This you can take those bottles, you can powderize them and use them as a pozzolan. And there's a spec for that, and there are people commercially providing that product right now in certain markets. There's also SEMs that are produced from carbon dioxide. So they actually will sequester carbon dioxide. Solidia SEM is one company. There's other companies that will basically carbonate fly ash as they grind it and use that as a product. There's one company called Terra CO2 that actually is manufacturing fly ash. They're taking rock and they will heat it up and turn it into glassy phases, such as shown in the micrograph in the far right of the picture there. And you ask yourself, how can that make any sense? Well, they do it locally, right? This plant is portable, so they can do it actually at a ready mix plant is what they're talking about doing. But again, all of that energy, all of the CO2 has to be accounted for. These are the guys processing carbon upcycling, fly ash process in a rich CO2 environment. And then there's a number of non-traditional materials. There's so many things going on right now, working with SEM technologies, blending, experimentation. And I know that you have one faculty member. What is his name again?
LaShawn Gard.
Yes, Dr. Gard. He's very active in this area, but this is very exciting, and I'll get to there in a moment. Because also there's an alternative cements. So we have a spec, ASTMC 1157. It's a performance spec. It's a spec that says we don't care really what you have in this hydraulic cement. What we care about is how it performs. So the traditional specs are largely based on oxide analysis in meeting certain physical properties of the material. This one will measure the performance criteria. And if you have a cement that works, it'll fit. And so one that we have recently used on Min Road was an ASTMC 1157 type 120. So they underground 20% limestone. And we blended that with 30% fly ash. You know, that mix had the highest strengths and lowest permeability almost of any mix we looked at. It was one of the best performers. We can go away from alkali activated hydraulic to actually geopolymers, which is a whole nother little intriguing area to play in. And then there are cements like Solidia that carbon sequester, where they create blocks with their cement. They cure them in a carbon dioxide rich environment to cause it to harden. So the hardening is actually the formation of calcium carbonate. And then there are some, these are interesting companies. They actually make Portland cement without calcining limestone. So sublime, brimstone, they use chemical methods, they use different sources. This whole area is ripe for innovation. I call it the blinky light, shiny blinky lights. For academics, they love this realm. You can play in the lab and create things. But there are a lot of questions that remain regarding the viability. Will these materials meet engineering needs? And more importantly, are they economically scalable? Portland cement sells for roughly 9 cents a pound. Okay? Used to be 7 cents a pound. Inflation, it's terrible. If you go to the store, you see it. About 9 cents a pound for Portland cement. Can you do this shiny, blinky light for 9 cents a pound? Can you do it for 10 cents a pound, 15, 20, 30? And when does it all of a sudden become non-cost effective to build civilization? So that's the issue. You can't divorce the economics from the environmental impact. And so this is where the rubber is really meeting the road. And so really, in the short term here, 3 to 10 years, what we got to do by 2035, let's say, we need basically to do what we're doing, and we need to do it a lot better. And then some of these other materials will start filling in and helping us out. The one potential bright spot on the horizon is Portland, is limestone calcined clay. How many of you heard of LC3? Come on, give me a raise of hands. 2. Karen Scribner. How many of you heard of Karen Scribner? 1. Well, Karen Scribner is, I don't want to give Karen too much credit, but she's one of probably 3 of the top cement people in the world, if not the top. But don't let Doug Hooten hear me say that. She's definitely a leader. She's advocating this. She's pushing it hard in a lot of countries in Asia. It's becoming a viable product where they're taking about 50% clinker. So we're not getting rid of clinker, but they're blending with kind of impure kaolinic clays and limestone at higher addition rates. And the papers are worth reading. It's worth investigating. This work is showing great promise and is scalable because these low quality catalytic clays are available pretty much everywhere. So from a scalability perspective, from a raw material perspective, they're very much available. And so these can be blended to meet the ASTMC 595 spec. So you can do a 1TL 15P35 if you're tuned in to the cool ASTM codes. And I will say, for those of you, again, most of you are students, if you work in this field, you will become very familiar with ASTM and ASHCO, and these will be the things that dictate your life in many ways. Or we could provide this as a ASTMC 1157. So in the US, there are currently no producers of this material. There are those that are toes in the water looking at it. So I think this is going to be something that we see more of. All of these things that I've talked about, they're possible. The problem is clinker is the heat in concrete, right? I think all of you have had a concrete class. Can I assume that? You should as civil engineers, because you ultimately will be using it, even if you're an asphalt person. You'll still need it to stabilize your base and your soil and build your curb and gutter and sidewalk. So it's an exothermic reaction, and it's what drives the SEM to work. If we pull clinker out, there's a lot of chemical reasons why this is true, but it's less heat. It's going to slow things down. Your setting is going to slow. Your finishing is going to slow. You won't be able to strip the forms as fast. You might not be able to open as quickly. All of these things cause contractors to like froth at the mouth, okay? Because time is seriously money. I've been told by a top floor slab producer in the US. They do, probably hundreds of floors a year. They say, look, we're not a construction company. We're a finance company with a construction group. They watch every hour of every worker on every project, and they monitor their productivity. And if I come in with a 1L cement, their productivity just took a 20% hit. Okay, this is very important to them. So we have got to figure out how to take clinker out and then meet these challenges. How do we do this? We're going to have to compensate. Are we going to come up with new admixture packages? Are we going to come up with new designs? This is challenging stuff. It's not as blinky and shiny a light as coming up with a new geopolymer, but it is the essential need for what we're going to need in our industry. The second strategy is even simpler. We just need to optimize our concrete mixes more. And since there are a lot of asphalt people, the concrete people are trying to take a page from the asphalt industry and basically create similar gradations using 3 or 4 aggregate bins, not just a coarse and a fine, and optimizing. And this is called a tarantula curve, because the person who invented this, Tyler Lay at Oklahoma State University, this looks like a tarantula. And this is just one tool of many. You can see the tarantula, right? It's got an air, in Tyler's mind, this is a tarantula. And this has been an amazing tool for slip form paving concrete that has to be able to mobilize and consolidate under vibration. And then as the vibration passes, it sits there and will stand up straight and tall. But what you get right down to, the similar tools that you have become used to with VMA, I think, Jeff, you were saying for your RCC work, you're actually looking at VMA. Same concept, right? Just enough void. We identify the voids, we reduce them, we put enough binder in there to fill the voids and a little bit more to provide the lubricity needed. And so these are our tools that we're using. A lot of people in the concrete industry, they'll swear more cement equals more strength. And it's actually a complete falsehood. This is data from NRMCA, National Ready Mix Concrete Association, showing 1 day and 28-day strengths for different mixes with different cement contents, holding water cement ratio constant. And what you see is not only, you don't see any change really in effective strength. And then you say, wow, but permeability, we need more paste to be less permeable. And again, what you find is actually the opposite in some ways, that the more paste we put in some ways we get worse permeability. So getting paste out of concrete is not only good from a carbon reduction standpoint. I started advocating for this back in 1998 for durability, right? The more paste we put in, the more alkalis, the more chance we have alkali-silica reaction. The more paste we put in, the more shrinkage we get, the more restraint cracking we get. It costs more. So why do we put more paste all the time in our concrete? And the reason is control. The reason is with more paste, a ready-mix producer can have their moisture levels fluctuate with less impact on the water cement ratio, and therefore less impact on strength. And since we pay on strength, the ready mix supplier, they're going to want to put more cement in to cover themselves. So this is a challenge, right, for the industry. We need to work good gradations, take those aggregate away from the asphalt people, get them into our concrete, and then basically work with our producers to better control their moisture. And it's not as simple as it sounds. This is some real data I worked with. This is Project Neon in Vegas. So if any of you go to Vegas and you drive on I-15 past the strip, this is real data showing 3-day flex rates. One mix had the colors changed. Awesome. Gotta love that. But the early mix, I know one of these buttons is the do not press button, and one of them is the laser. All right, I got the laser. Every one of these has a do not push button. Just remember that if you're up here. So the early data here, that was all stuff with 500 pounds per cubic yard, and it was being placed in February. And if you look at that data, you may in your mind imagine, maybe at 3 days we had slightly lower flex rates. But look at those flex rates. That's at 3 days. If you look at the 28-day, effectively no difference in strength. And also, again, ridiculously high strengths. And this is field-produced concrete with field-produced beams tested in the field. So all of the variation due to that. So Project Neon was the minimum cement content allowed in Nevada to this day is 611. We were able to get them down to 500 on this project as an alternative technical concept. And it worked very well. I'm going to wrap it up here quickly. I want to at least leave 10 minutes for questions because you're not going to be able to hide, even though some of you look exceedingly bored, but we'll keep you going here. Basically, assessment is really the key. We could talk a lot of talk. We could say, boy, this is a low carbon binder. We could say this is zero. Heck, you guys are probably not aware, if I put 35, 40 pounds of biochar in my concrete, I'm almost carbon negative, right? It's true. That's another story. But we need to assess. We need to basically get away from the greenwashing, the claims, the labels, and we need to measure. And the way you do that is through standardized assessment based on life cycle assessment, ISO standards, and doing environmental product declarations. How many of you, honestly, have heard of an EPD? All right, good. We're making progress here. EPDs are essential to what we need to do in the future. And basically, these are some real data from EPDs. This is where we stand in the US. So the average cement in the US, as I said, about 922 kilograms per 1,000 kilograms. Holcim St. John, I bring that one up because I use this one on a project. Their 1-2 is at 748. Their type 1L 8%, I think they've now gone up to 12. That was one of their first, was at 724. You'll see another cement type here, calcium sulfoaluminate. That's lower. Fly ash is at 12. That's just basically digging it up with a backhoe, putting it into a truck. Okay, that's what fly ash is. And then the pozzolan, the urban mining ground glass, that's at 55.9. But you can start seeing how you can use these numbers to actually do something quantitative and meaningful, right? This shows basically an EPD from the Minroad project. This was a standard Minnesota DOT paving mix. I didn't know you guys came with spiders. Be free, little friend. All right. Little spider just got let go there. You didn't catch that. But basically, so what you see in this mix at 220, this data on the left in this box plot shows the US kind of average is that, that blue line or purple line. Things always change colors when you project them. This box represents conservative to achievable results, and the MnDOT mix just out of the gate was here. Their standard mix had 570 pounds of the St. John 1L8 with 30 pounds of or 30% fly ash. And we did another mix on that job where we pulled out 70 pounds of cementitious. So it's way down there, right? It's all the way down. So it shows what can be done when you have an EPD and you start to optimize. So I'm going to this is what should perk some people's ears up, funding opportunities, right? FHWA Climate Challenge. I'm told, Errol, you guys got a climate challenge, right? A lot of states did. 27 projects were awarded. I want to note every single, what's that?
You got one too.
Yes, that's what I said. So Errol, you got one. Yeah, but there's 27 of them. Every single one who applied got one. Hey, I'm going to tell you something, my friends. If you have a trough of money, then all you got to do is go up to that trough and eat from that trough. You should eat. So 27 people were smart enough to go eat out of that trough. That's awesome. There's no disgrace in that. That shows that's smart. Basically, IRA is coming out soon with $2 billion of funding that's going to be specifically designated towards low carbon materials for federal highways, and 1.8 billion is going through GSA. All right, this is some serious coin. This is additional money beyond what a project would cost. If you do the math on this, it's about $40 million per state, and it's for asphalt, concrete, glass, and steel. I'm assuming the asphalt people aren't going to go for any of this. They're going to go for a lot of it. And the concrete people are going to go for a lot of it. I throw these up here because this is where you can track it. So if you are looking for funding, it's going to require partnering with your state DOT. So it's going to be a program that right now, I would speculate the Illinois DOT doesn't even know about. Most DOTs do not even know about this program. And it's a multi-year program, so you could come in with a 4-year program. You could ask for $20 million. The only thing is, every DOT gets one bite at the apple, I'm told, one application. So the mod, the asphalt guys, and Jeff, the concrete guys, will need to get together, be nice to one another, and go after this money together. So you're going to see the announcement later this month or early next month. Applications are coming out in December. And you'll have about 3 months to do the application. That application, Errol, is going to be very similar to the one for the climate challenge. It is not going to be a complicated application. It's going to be basically a grant. And so it will buy equipment. It will pay for engineering. It will pay for consulting. Thus, I'm interested. It will pay for partnerships between industry and universities to help the state move towards lower carbon materials. The one thing is they have to be linked to specific projects, and that's doable. And then you have to demonstrate carbon reduction, and it will require EPDs. So I'm working with a team on the concrete side with my old firm, NCE, Larry Sutter, Doug Hooten, Al Innes, myself. And then we have been funded by ClimateWorks Foundation and Breakthrough Energy Foundation to support the creation of a reduced carbon concrete consortium. Originally, we had low carbon concrete consortium, but then we realized it conflicted with LC3. So Karen Scribner has rights to that. So we're the RC3. We're basically, looking to work with agencies, and we have a number of people already lined up and interested. And obviously, if you guys are looking at involving Illinois DOT, we'd love to partner with you. We recognize that universities are going to be a key element of this, but it's not solely for universities. And basically, Ahmad, I'm sure we'll have a chance to chat about this a little bit more. And I've already talked to Jeff a little bit about it. So some closing thoughts. Low carbon to carbon negative concrete is really challenging, and it's also an opportunity. And most of you have probably not spent much time in this industry, but trust me, when you get out there, you're going to see this is not an easy lift. Even moving to 1L cement was not an easy lift in some markets. And that was easy lift. There's going to be a challenge. People's cheese is getting moved. If you have not read this book, I highly recommend you get it. It's a very simple little book. Who Moved My Cheese? It's a story about an entertaining little mouse that cheese would always show up in the same place every day. And one day he shows up and his cheese is gone. And how he responds to that situation. Because a lot of people's cheese is going to get moved in the next 5 years. And so you want to be the mouse that figures this out and not the mouse that panics. It's going to be a major shift in the way we think, the way we approach, the way we design. Whereas before, it's just Portland cement concrete, 15% fly ash, 570 pounds, total cementitious. You're going to find yourself working with all kinds of innovative materials, innovative solutions. Civil engineers need to be knowledgeable, and we need to be leading this implementation effort. We cannot be the one sitting on the back burner. And I hate to break this to you, but you guys you're at the tip of the spear. You're the best of the best, right? You're here in one of the top programs as a graduate myself in the country, if not the world. And what about everyone else who went somewhere to some other school? For all you people online who aren't Illinois grads, I know how bad you feel about that. You can always come back for grad school. Bottom line is that civil engineers, we have got to lead this effort. And that's the people you're going to be working with. So, in summary, we know greenhouse gas emissions are concentrating in the atmosphere. They're going up. Climate is changing. And the overall impact, the overall impact of concrete is huge. It's a big contributor to this. It has put it at the focal point of governments world over, and the industry is responding. There are strategies that we talked about that we can do right now to immediately reduce our carbon footprint. Most everything I talked about today can be implemented on projects and are being implemented around the country by people that are already plugged in and are thinking about this. We just need everybody to start thinking about this. We got to rigorously verify to avoid greenwashing. EPDs are going to become common. If you're in Colorado right now, you have to have an EPD on a job. I'm trying to remember the dollar value, but is it like $1 million? I don't know what the number is, but it's not a big job. You have to have an EPD in Colorado right now on a paving job. And there's a lot of funding available, a lot of opportunity to advance this. And then the final point is we're definitely hiring. We're hiring in this area. We're hiring in every area, in every office right now. So we are looking for good people. I've already mentioned that to Jeff, Ahmad. I'm not sure if I mentioned it specifically to you, but any of you professors, send your people our way. We're looking for them. And then the final thing, this is a Larry Sutter thing, be decisive. Right or wrong, the road of life is paved with flat squirrels. So make a decision. Do the right thing. Don't be indecisive. And then, the final, just for questions. I like this one because that same hippie is a little bit older, still holding the same sign, but, this is just the beginning. This is not the end of concrete. This is actually a time of great innovation. I think it's what we need to get out of our complacency and actually create, the best building material in the world for millennia to come. So, and this picture I took in, this is, what island was that in California, where that's a horse hoof print in about 100-year-old concrete. So somebody's horse got loose, stamped itself into that concrete pavement. So this is where I didn't give enough time, but some questions. Questions are very good things to do.
But we may have time for like one very, very quick question.
I thought I had an hour.
Does anyone have a question for Dr. Madam now? Sure. Okay, Professor.
Excellent presentation, Tom. I enjoyed very much. I was going back to your alternative cementitious materials that you pulled up and about the reclamation materials and things. Like from the coal combustion industry, I know those CCP's products, there's already a lot of bottom ash that's not used. So why people go to reclamation side instead of getting the newly produced ones? More bottom ash to use like that.
Bottom ash is going to increasingly be used now that it's allowed under spec.
Yeah.
You're going to see that's this one probably here. With the spec change, it's now completely allowable. So bottom ash, both newly produced as well as that commingled in landfills. The problem with landfills, right? You didn't separate fly ash from bottom ash. They commingled it in the same landfill or pond. And so you will increasingly see use of all kinds of material. And I would say, Errol, in your work with the stone industry, some of those byproduct materials, those crusher fines, with little processing, might be able to make a very good SCM. And so they really need to be looking at their chemistry and their mineralogy to see what it would take to produce SCMs. So a lot of opportunity. And I'll stay around if we got to end the thing here. So
yeah,
He's running a tough ship here, man. What is that? I was watching that clock. All right, go ahead.
Okay, so let's thank Dr. Van Dam for this presentation.